Assalamualaikum and hi to everyone. Thank you for watching this video. So this video will continue on the piece description, one of the characteristic of the sine wave. Before this, we already discussed what is the frequency and what is the period. So in this video, we'll discuss more on the piece, composite signal, and so on. So piece describe the position of the waveform relative to time zero. So it means is the started or the beginning of your waveform, and it's measured in degrees or radian. So 360 degree equal to 2 pi radian, 1 degree equal to 2 pi over 360 radian, and 1 radian equal to 360 over 2 pi. So this is the formula on how to do conversion based on degree into the radian. Okay, phase change. Okay. What's the meaning of phase? Describe the position of the waveform relative to time zero. So relative to time zero. Okay. At this point, based on this wave, sine wave, there is no phase change. Everything is in the cycle 1, 2, and then equal. For B, it begin with the 0 at 0 degree. Okay, and it change from 0 to 90 degree. So 90 degree phase change. For C, it begin with 0, but suddenly it come from this point. So we call as 180 degree phase change. At this point, okay, it's starting at 0, and suddenly it change from this point. So we call as 270 degree phase change. So phase is referred to this starting point that relative to 0 time. Okay, this one is another example for phase. This graph show that we have 0 degree of phase. For this one, we have 90 degrees of phase, 1 over 4 cycle. Okay, this one we have 180 degrees phase, and this one we have 270 degrees. So based on the position of the starting or the beginning of your sine wave. So this diagram show you we have 3 sine wave. The amplitude is similar. The frequency also similar. But the difference at the pieces. This one start at 0 degree, this one start at 90 degree, and this one start at the 180 degree. Okay, example here, let's say you have a sine wave is offset at 1 over 6 cycle with respect to time 0. What is the piece in degree and the radian? So we know that one complete cycle is equal to 360 degree. Therefore, 1 over 6 cycle is equal to 1 over 6 times 360 degree. Then you will get 60 degree. So your 60 degree convert to the radian value. So 60 degree times 2 pi over 360 radian. So equal to pi over 3 radian. So this one, when you use calculator, you will get it's equal to 1.046 radian. This figure show you the time domain and frequency domain plot for sine wave. This means if you have a sine wave, then you can represent your sine wave in two form. Either you can use the time domain. Okay, this one is time domain, or you also can use the frequency domain. So time is referred to this one, and frequency is referred to this value. So a sine wave in the time domain, we have the peak value 5 volt, frequency 6. Okay, 1, 2, 3, 4, 5, 6. 6 cycle in 1 second. So we can identify that we have 6 hertz. So these are the difference. So you should know how to differentiate between the time domain as well as the frequency domain. A complete sine wave in the time domain can be represented by one single spike in the frequency domain. Okay, this one is single spike. So the time domain and the frequency domain of three sines wave, okay, we have multiple wave, and how to represent the multiple wave in a time domain, and how to represent the three wave in the frequency domain. So if we have three wave, so it will look like this one. We have the blue color, this one with the zero frequency, because it is a straight line and the frequency doesn't change at all. At this point, we have the pink color and we have the green color. So pink color with the frequency 8, the green color with 16. So in frequency domain, okay, the X plot here is the frequency. So we have blue, pink, and green. Based on this one, you can convert to this one. Based on this one, you can convert to this one. A single frequency wave is not useful in data communication. So usually and commonly, we need to send a composite signal when we do transmission of signal. So a signal made of many simple waves, as I mentioned before. Composite signals mean that we have multiple signal in one signal. So based on the Fourier analysis, any composite signal is a combination of simple wave with different frequencies, amplitude, and phases. Okay, if the composite is periodic, the decomposition give a series of signal with discrete frequencies. I mean periodic, so we have the pattern. So we can have the series of discrete frequencies. However, if the composite signal is non-periodic, I mean there is no pattern at the signal, so the decomposition give a combination of sine wave with continuous frequency. Okay, example here, figure 3.9. Okay, this figure is the composite signal. So the frequency we have 1, 2, 3 if in 1 second. Okay, this type of signal is not typical of those found in data communication, and we can consider it to be a 3-alarm system, and each with a different frequency. So the analysis of this signal can give us a good understanding on how to decompose a signal. So this one is just example about the composite signal, a periodic composite signal. So when we talk about periodic, it must have a pattern. Okay, decomposition of a composite periodic signal in the time and frequency domain. Okay, when you have a composite signal and you try to decompose that composite signal, it will give you multiple sine wave. So when you represent the multiple sine wave in the time domain, it will look like this one. So in your one graph, you will have multiple sine wave. So you can identify based on the color and the frequency. So those three sine wave have different frequency. Okay, the next graph here is the graph of frequency domain that show you in frequency base. So basically this one is not the right one. Supposedly is a frequency, not the time. Okay, example 2. Okay, this figure show you about the non-periodic signal. Non-periodic signal. So it can be signal created by microphone or telephone. When you say a word, so it will give a sine wave. So in this case, the composite signal cannot be periodic because that implies that we are repeating the same words or words with exactly the same tone. The same tone, same word, so the signal is quite similar. So this is how we represent the non-periodic signal in time domain and frequency domain. Okay, it look like this one. There is no cycle pattern, And for frequency domain, we cannot have the exactly frequency, so the data is continuous. Okay, next, you already know phase, frequency, amplitude. The next part, you should know what is the bandwidth. Okay, bandwidth of a composite signal is the difference between the highest and the lowest frequency content in that signal. So that means in a signal we have the frequency, multiple frequency. So in order to identify the bandwidth, you need to know what is the highest frequency and what is the lowest frequency. Then the highest frequency minus the lowest frequency, then you will get the total of bandwidth of that signal. Okay, example here. The lowest frequency we have is 1000. The highest frequency that we have is equal to 5000. So the bandwidth 5000 minus 1000 equal to 4000 Hertz. Okay, this one for periodic signal and this one for the non-periodic signal. So you can draw the spectrum of the frequency. Okay, identify the lowest frequency and then identify the highest frequency, and then just subtract from the highest, subtract the minus frequency, then you will get the total the total number of bandwidth. Okay, example here. Let's say we have a periodic signal and then we decompose into 5 sine wave. So the frequency 100, 300, 500, 700 and 900. What is the bandwidth? So you find the lowest frequency, which is referred to 100. The highest one is referred to 900. So 900 minus 100, total bandwidth equal to 800. So based on this formula, and then draw the spectrum, assuming all components have maximum amplitude 10 volt. Okay, so you need to draw this frequency domain. Amplitude is 10 volt, and then the lowest is 100, the highest is 900, and then minus, you get the bandwidth. This one is the spectrum when you ask to draw the spectrum. Example number 2. A periodic signal has a bandwidth of 20 Hz. The bandwidth is given to you. Okay, so the highest frequency is 60 Hz. What is the lowest frequency? So 60 minus 20, then you will get 40 Hz as the lower frequency. Okay, and then draw the spectrum if the signal contains all the frequencies of the same amplitude. So assume that all the amplitude are similar. So you can draw something like this one. The lowest is 40, the highest is 60, total bandwidth is 20, and all have the same amplitude. Okay, the next example, a non-periodic composite signal has a bandwidth of 200 kHz. So total of bandwidth is 200 kHz. So at the middle, the frequency is equal to 140 kHz. And then it has the peak amplitude 20 volt. The two extreme frequency have an amplitude of 0. Okay, the frequency is 0. And draw the frequency domain of this signal. So based on the information given, okay, bandwidth you have 200. At the middle you have 140 kHz. So 140 kHz at the middle. So that means the maximum frequency is 140 plus 100. The minimum is 140 minus 100. So the lowest is 40, the highest is 240. So based on that part, you can draw a spectrum. So the lowest part you have 40, the highest part you have 240, and then at the middle you have 140. Two extreme frequency at 0, this one, and this one is the highest part. Okay. So next video we'll discuss on the digital signal.